Welcome everybody to today's public lecture in celebration of the National Science Week and brought to you by the Sydney Mathematical Research Institute. So my name is Oded Yacobi. I'm a professor here at the University of Sydney, and I am delighted to see so many people here today for this public lecture, and I'm delighted to be able to introduce today's speaker. So before we begin, I just want to acknowledge that we're meeting on the traditional lands of the Gadigal people of the Eora Nation to pay respects to their elders, past, present, and emerging. So our speaker today is Associate Professor Zsuzsanna Dancho, Zsuzsi, as we like to call her, and she's also a professor here at the School of Mathematics and Statistics. Zsuzsi did her bachelor's degree at Eötvös University in Budapest, where she's from. She did her PhD at the University of Toronto, which is actually where we met, I think about 15 years ago. After her PhD, she was at some of the best mathematical institutes in the world, including, I think if I get it right, the Institute of Advanced Study in Princeton, Fields Institute in Toronto, the Mathematical Science Research Institute in Berkeley, a postdoc at the Australian National University, before arriving here in Sydney. And Zsuzsi is a quantum topologist. She studies knots, which you'll hear about today. She's done a lot of work in this area and a prolific researcher and also a fantastic communicator of mathematics, as you guys will get to see very soon. Her number file videos on YouTube, I just checked this yesterday, have well over 2.5 million views. So probably some of you have seen those. So before we begin, I just want to share one little story from when I first met Zsuzsi back in Toronto. I remember she had a Christmas party in her place, and it was one of those secret Santa things. And so after we exchanged gifts, she had us all hold hands with the person that you gave the gift to and the person you received the gift from, thereby forming a human knot. And then she proceeded to tell us properties of this knot. And I knew from then on, Zsuzsi is very serious about knots. So I'm very happy to give you the stage, and let's welcome today's speaker, Zsuzsi Dancho.
Thank you so much.
Yep.
Thank you so much, Oded, for that wonderful introduction, and for Catherine and Stefan from the Sydney Mathematical Sciences Institute for all the help that I have had preparing this talk. Before we get into it, let me get to know you just a little. Could you put up your hand if you're less than 12 years old? A few. 12 to 18? Quite a few. Over 18 and haven't done any math since high school. Yay, welcome. And over 18 and have done some math since high school. Many people, all right. I hope I have something for all of you, including those under 12 and those who haven't seen any maths or done any math since high school. There's 3 math words in the title, and we're going to get to all of them, but I'm going to start with my favorite one, and that one is knots. Knots are all around you, all around nature. For example, in living organisms, in our cells, our genetic material is encoded in these long, long molecules called DNA, or in some organisms, RNA. And these molecules form this double helix, this spiral structure. When the cell wants to multiply, what it does, it cuts this spiral along the middle, and then the 2 halves have to go to the 2 new cells for the cell to be able to multiply. But because the helix is twisted, these 2 long, long halves are going to be knotted up with each other, and the cell has to separate these in order to be able to form 2 new cells. So some antibiotics, for example, work by inhibiting this process, inhibiting the enzyme which helps the cell do this. And biologists study all the possible knots which can come up in our cells by the DNA knotting with itself. In engineering, knots are used to create super strong materials by almost in a knitting fashion, knotting together long strands of polymer so that the material becomes very, very hard to tear. And in mathematics, Knots are very important because they give us a lot of information about the structure and properties of all three-dimensional spaces and shapes. So how do mathematicians think about knots? The key question that mathematics can help us answer about knots is whether two knots are the same. And that sounds like a simple question, but it's actually a really hard question, which I hope I will explain by the end of this talk. But first, we have to understand what we mean by being the same. Mathematicians really like to know what we're talking about. An example, a piece of evidence is that my 9-year-old here uses the word well-defined in casual conversation. So what does it mean for two knots to be the same? If I turn around, has my genetic material changed? No, right? Here's my scarf. It's folded up. If I do this, has the knitting pattern changed? No. So we have to somehow agree on when we consider two knots the same. And for example, if they are in a different location, if they are oriented differently, or if you can gently massage one of them to look exactly like the other, then we say that two knots are the same. And in particular, a very important basic case of this question, a simple type of this question, is when you want to decide, you look at a complicated knot and you try to decide whether you can gently manipulate it to turn it into a completely unknotted piece of string. How many of you celebrate Christmas? How many of you have tried to set up a Christmas tree with Christmas lights? Yeah. So when the Christmas lights come out of the box, they don't look like they are unknotted, right? they look very much knotted. But then, as you gently manipulate them, you turn them into this unknotted piece of string or circle that you can then put on the Christmas tree. So for more complicated situations, it might not be obvious. If it hadn't been for you putting the Christmas lights in that very box the previous year, you wouldn't necessarily know that it's possible to do it. And in many cases, we don't know whether it's possible to do it. So in order to be able to study this question, we have to really pin down what it is that we mean by a knot. And in particular, if I say knot, most people's first thought will be your shoelaces, for example. But mathematically, your shoelaces are quite boring knots. And that's because when I put a knot on a piece of short string, I am always able to pull out the end, right? The way I put it in, I can pull it back out. And so a knot on a shoelace or a short string can always be undone. I can always pull it out. It is always the same as just a straight piece of string. Not interesting. Mathematically, it's always not a knot. In mathematics, we call it the unknot. However, there are related knotted things that are interesting. Imagine that you put a knot on your shoelaces, and then they are stretched out to super, super long, to infinity on both sides, or extremely, extremely long. Then I can't pull it out anymore. And this is the situation that happens with strings of DNA. Even though those are finite, they are extremely skinny compared to how long they are. And so if they get knotted up, they can't necessarily get unknotted by pulling out the ends. Similarly, if you put a knot on a short string and then you glued the ends together, or if you imagine one of those extension cords, you can plug one end into the other and close it up into a circle, then again, I can no longer pull the ends out. So these are the kinds of knots that we think about in mathematics, the ones that are on infinite strings and the ones that are on circles. So here's a knot on a circle. And I would like you to look at it for a couple seconds and try to figure out whether you can unknot it or not. Let's try to decide this by democracy. Who thinks that this knot can be undone? It's just a straight up circle. Quite a few people who thinks it cannot be. It's an actual honest knot. If I were a sailor, I would trust this knot. Yeah, great. Okay. So democracy skews towards undoing it. So let's try. Let's try to manipulate it. So see that little bit of string that is highlighted, we are going to push it up, like stick our finger in and push it up behind the next part of the knot. And then we're going to pull it a little bit further so that the next two bits connected to it also come up. And that little piece now is just poking down. We're going to pull it up further. And then see that whole bit is behind everything else. So I can put it up, further up, behind everything else, behind all the other strings. And now that it's all behind, I can pull it out here to the right. So I get this long thing to the right. And now this long thing is over everything else. So I can pull it into that region in the middle. And now you can see I can pull it further out behind that other string. And now I basically just have two little kinks. I can pull the kinks apart. Kinks pulled apart. I can untwist it, and it's a circle. So if that was too fast, here's the whole sequence. So we have proven beyond doubt that this knot can be unknotted. And we have done so by demonstrating how, right? We have done it. But the hard question is, how would we ever prove that a knot cannot be undone? How is that ever possible? Because if I spend 2 days trying to undo a knot and I don't succeed, have you ever had trouble with your headphone cord or your Christmas lights, and your kid or your friend or your parent comes up to you and says, you're doing it all wrong, let me do it? So maybe if I fail, you could succeed, or maybe he could succeed. We'll never know for sure. If we all fail, it's all just evidence, it's not proof. Mathematicians, we really like proof. So we have invented, not me, mathematicians long before us, before any of us were born, invented a type of mathematical machine which we can use to prove beyond doubt that a knot can never be undone. And this kind of machine is called a knot invariant. So I need to tell you what a knot invariant is. It is a machine into which we feed knots and outcome numbers. But there's a very important thing without which a knot invariant is useless, and that is that if two knots are the same number has to come out. We have seen that these two knots are the same because the top one is the one that we just undid. The bottom one is the undone picture. So these two are the same. If I plug them into my machine, the same number has to come out. That number is 1. Also, if two knots are different, it might be that different numbers come out. If I see that different numbers have come out, I can be absolutely beyond doubt 100% sure that those inputs were different knots. And that's because had they been the same, this machine would give me the same numbers. Now, if two knots are different, I could get unlucky, and it could be that my machine's just not good enough, and it still gives me the same value. So this is an example. This machine is an actual mathematical thing. It's called the determinant of the knot. And for these two knots, it gives the same number, even though that top knot is not actually unknottable. We know that because we have better invariants. So sometimes we need invariants that will give some more complicated values, not just numbers, but maybe polynomials, maybe vector spaces, groups, but we don't need to talk about that. So that's what an invariant is. And mathematicians have used invariants over the years to try to classify knots. essentially building like a periodic table of knots, just like we have a periodic table of elements. And those two things are more related than you would think. In the 1880s, Lord Kelvin, physicist, the one that the degrees Kelvin are named after, he had a theory that atoms are knotted little pieces of string in the ether. And he asked mathematicians, including this guy Tate, whose picture is on the screen, to try to classify knots in an effort to classify atoms. So he wanted to build a periodic table. And Tate did this. Now, of course, it turns out that atoms are not knotted pieces of strings in the ether, so that didn't work out. But just like in many examples of basic research, knots did find their applications 100 years later elsewhere in nature. Tate, in 1885, classified knots up to 9 crossings. And this is a table of the first few. And he had very, very limited access to any sort of invariance. So it's somewhat amazing that he was right about all of his decisions of which knots are the same and which knots are not. So here's a table of knots up to 10 crossings due to Brian Gilbert and Dror Barnatan. Today, knots are classified all the way up to 20 crossings. And the record holder is Morven Thistlethwaite. And that is a paper from earlier this year. Before that, the previous record was held by Australian mathematician Ben Burton, who's at UQ, University of Queensland. So I'd like you to give me a guess for how many knots there are up to 20 crossings. So you can see all the knots up to 10 crossings here. 20 crossings is about double that, so try to guess. Who thinks that it's more than 200? Lots of people. Who thinks it's more than 1,000? 10,000? 100,000? Million? Billion? Great. It really grows. So there are 2,199,471,680 knots up to 20 crossings. For the mathematicians, these are just the prime knots. And scientists use this knot classification and knot invariance to distinguish knots in the scientific scenarios where that is necessary. So at the end of this talk, I will teach you how to build a specific knot invariant and a very good one. But before that, we have to talk about our main tool, which is graphs. Graphs come from a completely different area of mathematics called combinatorics. And first, we have to, again, agree on what we mean when I say graphs. I don't mean the graph that you learned about in high school, where it's the graph of the sine function goes like this. That's a kind of graph. This is a different kind of graph. It's a synonym for the word network. Network is more of a computer science-y word, and graph is a little bit more of a mathy word. So we like to use the word graph. But it's a very simple structure which encodes a surprisingly huge amount of complexity. So what does a graph consist of? It consists of some nodes, which we also call vertices in maths, and then some edges, which are the connections between the nodes. So the picture that you see here is a picture of the Paris metro system, which we're all very jealous of. So how do we use, this is a model, right? This is a graph. The nodes are the stations, and the edges are the train connections, the metro connections. How do we use this graph in real life? I arrive in Paris, say at Gare du Nord, which is that big junction in the north side of Paris. And then I want to go straight to the Eiffel Tower, which is down here on the south side of the River Seine, just under the little curve on the left. So I look at my graph, and I figure out that I have to take the blue or the green line all the way down to the south side of the river, and then the yellow line along the river until I get to the Eiffel Tower. So we all use graphs in our day-to-day life. But graphs are super versatile, which is a feature of their simplicity. And they can be used to model lots and lots of things. One of those things is social networks. There we go. So this is a baby social network. You know Oded, and you know me. This is a social network with 2 nodes, and there's an edge because we know each other. Let's grow this graph a little bit. This is my son, Oliver. Oliver, you can wave. So we know each other. So Oliver and I have an edge between us. But also, Oliver and Oded know each other. Oliver loves Oded's quesadillas. So they also have an edge between them. And then for the 4th point on this graph, 4th node of this graph, I attempted to put the most famous person I know. Hands up if you know this guy. Great, a few people know him. Anybody want to shout?
Nash.
Yes, John Nash. Great. Anybody seen this movie? Yeah, Beautiful Mind. So he is a Nobel Prize winning economist and mathematician, and the founder, or one of the founders of the entire area of game theory, which is very important in modern economic theory. And the way I know him, it's a little bit tenuous. As Oded said, I spent a few years at the Institute for Advanced Study in Princeton, which is a research institute, and it's adjacent to Princeton University, where John Nash works. And the IAS, the institute, serves really nice lunches. And John Nash comes over and has lunch there and sits down at random tables with that semester's crop of postdocs and visitors and has a little conversation. So I've had a little lunch conversation with him. I would like you to remember the edge of John Nash, because that's a very special kind of edge on a graph. In graph theory, it's called a leaf. It's hanging off there without any further connections, only a connection to one vertex. So this is a baby social network, but real social networks are much more complicated than this. This picture is just one person's network of Facebook friends, one person. So imagine all of Facebook, and that's just Facebook. Imagine all of all social media, or in fact, all of all humans with all of our connections. It is an extremely complicated giant graph. So what do graphs have to do with knots? Remember, our goal is to learn something about knots using graphs. And we're going to do this by this neat trick of building a graph out of a knot. This is actually a very old trick. We'll use it in a new way. But the trick itself goes all the way back to our old friend Tate, to the beginning of knot theory. So what do? We take a knot. First, we have to color it in. So we checkerboard shade it. When you play on a chessboard, the chessboard has white fields and black fields. And the white fields and the black fields are always adjacent to each other. You never have a white field touching a white field along an edge, right? And then the fields that are diagonally adjacent are always different colors. So always white diagonally adjacent to black. So we shade in the picture of the knot in the same manner. So I used light blue and white. Every region of this picture of the knot is adjacent to a different colored region and diagonally adjacent to a same color region. Can we see that? So once we shaded it in, next we're going to put nodes in all of the shaded regions. So here we have 3 shaded regions, and so that's going to be 3 nodes. And then the edges are going to correspond to all the places where the knot crosses over itself, where you see the string crossing over itself. At each of those crossings, you can see 4 regions, 1, 2, 3, 4. 2 of those are shaded, so 2 of those have nodes in them, you're going to connect those nodes. So there's going to be a connection, an edge in this graph, across every single place where the string crossed over itself. So from that knot, this is the simplest knot which cannot be undone. It's called the trefoil knot. From the trefoil knot, we built a graph, and that graph is just a triangle. Of course, we can do this for any sort of knot. So here's a more complicated one. So for this knot, we shaded it in, and we get 1, 2, 3, 4, 5 shaded regions, put a node in each shaded region, put an edge across each of the places where the knot crosses over itself, and we get this graph, which is like a little house on its side. So it's a square with a triangle attached to it. This can be done for any knot picture. But is this a knot invariant? What does it mean for something to be a knot invariant? Let's remember, the most important thing, if I feed in the same knot, I'm going to have to get the same value. Now, the values here wouldn't be numbers, right? Because what we have constructed is a graph, not a number. So what we want is same knot put in, same graph comes out. Is this a good machine? It's bad. Not good. Why? Here's 2 knots that are the same. You can tell that they are the same because the only difference between them is I put a tiny little twist on one of them. But that little twist doesn't change the structure of the knot. That's a gentle manipulation. I haven't done anything violent like cutting it up. So those 2 knots are mathematically the same, and for all intents and purposes practically the same. However, when I do this whole process, the little kink that I put on it is going to get its own shaded region. That shaded region will get its own vertex, and that vertex will get its own edge. And that's a John Nash edge, right? It's hanging off there with no other connections, just like John Nash in our little mini social network. These 2 graphs, are they the same graph? No, they're not. They have different numbers of vertices, different numbers of edges. They are manifestly different. So I have fed the same knot into this machine, and I got different graphs. No good. It's actually also bad in the opposite way. If I feed in different knots, I can very easily get the same value. And that's because when we constructed this graph out of the picture of the knot, we never took into account, at each of the crossings where the knot crossed over itself, we never took into account whether it's like this or like this. So if I swap it, then I get the same graph. It makes no difference. And that means these 2 knots, for example, I did one swap. You see the highlighted yellow region? At that yellow region, I just swapped one crossing of the trefoil knot. But by swapping that one crossing, suddenly this knot is unknotable. Because that part of the knot that includes the yellow crossing and also the one to its diagonally to the left, that whole part could be pulled over to your right. And that way you can unknot this knot. So I feed in the trefoil and I feed in the unknot, and I get a triangle in both cases. So this will not give the same answer for the same knot, and it will also not give different answers for different knots. Not very good, right? So it's true, this is not very good as is, but we can fix it. And the point will be to fix it. By the way, some of you have arrived early enough to get an activity sheet. And on that activity sheet, you can practice this knot graph conversion on a few cool examples. So let's get to the hard work of fixing this thing. How do we fix it? A partial fix to both problems is to restrict our attention to a nicer subclass of knots. And this nicer subclass of knots is called alternating knots. What does it mean for a knot to be alternating? It means that as I follow the circle around, I will always go under and over the string in an alternating manner. So start out somewhere, say here in the bottom, and follow it around and just say whether you go over or under. So we go over, under, over, under, over, under, and so on and so forth, over, under, until we get back to where we started. This is an alternating knot. Now, why is this good? First of all, we can no longer flip crossings. So that badness goes away, because if I flip the crossing, this knot would no longer be alternating. And also, the manipulations by which I can move the knot around are a bit restricted if I'm going to have to keep this picture alternating. So there's some hope that we'll end up with a knot invariant, which if I feed it the same knot, it gives me the same answer. But it's still not quite there, because I can do this twist trick in a way to preserve the alternating property of a knot. So the trefoil knot is alternating. You can take a second to look around it and see that it goes over, under, over, under, over, under. And when I twisted it, if I twist it the right way, it's still over, under, over, under, over, under, over, under. So these are alternating knots. They're still the same because they only differ in this twist. But they still lead to different graphs when we perform this procedure. So not good enough. But the question that I want us to think about together is whether we can make this into an invariant by some strategic forgetting. The problem with this Tate graph thing is that it retains too much information. I can do little gentle things to my knot, and it will remember those gentle differences, like a little twist. I don't want it to remember that. I want it to remember a bit less about the knot, so that when I gently manipulate the knot, the value would stay the same. So I want to start with the graph, and I want to forget a bunch of stuff about it. And you know right away that part of the things that I forget must be the number of vertices and the number of edges, because these two outputs have different numbers of vertices and different numbers of edges. So how can we do that? How can we forget how many vertices there are, how many edges there are, and still have something that makes sense? To be able to talk about that, we first have to talk about graph cycles. So what's a graph cycle? It's a very simple concept. It's just a closed path in a graph. How many of you like to go to the snow? A few. I lived in Canada for a large part of my adult life, and in Canada you don't go to the snow comes to you. But here we go to the snow, and sometimes we succeed. And the easiest access to the snow from Sydney is through Jindabyne. So you have to drive to Jindabyne. And this graph that you see on the screen is a picture of the road network, which is a little sparse, around the town of Jindabyne, or Jindy as the locals call it. So there's Jindabyne. There's this pink circle and the yellow circle. These are cycles in this graph whose nodes are road junctions and whose edges are roads. The cycles in a graph are important, for example, when you're modeling road networks or transport networks, because the more cycles you have, the more robust that network is. So imagine, for example, you live in Jindabyne and your grandma lives in Berrydale. My grandma lives in Budapest, so graph cycles are not so useful there. But in this scenario, let's say every Sunday you pick up groceries for your grandma and then deliver them to your grandma's house. Now, what if one Sunday a tree falls over the road that goes from Jindabyne to Berrydale, then you still have this longer way, because of this pink cycle in the graph, to get to grandma. If it wasn't for that cycle, if there was no cycle, including that edge from Jindabyne to Berrydale, you'd be out of luck, and grandma would be out of luck for groceries. So cycles are important. Here's a very robust network, right? If the yellow line is down in Paris, then we could start at Gare du Nord and just go down to that green line and take the green line over, and we can get to the Eiffel Tower. So how do we use graph cycles to understand knots better? Let's look at this one example. You remember this was the Tate graph of one of the knots. We got it from one of the knots. This is the house on its side. This graph has 3 cycles. One of them is this blue one. Let me call that cycle 1. So I go around up and down and to the right. Your left. The other one is this pink one, the rectangle. So we go up and over and down and over. That's C2. And then I have a third one, C3. That's the purple one, which goes all around the outer edges. Bum, bum, over and back. But these 3 cycles are not independent of each other. So intuitively, if you think about adding together C1 and C2, what you would get is C3. Why? Because I would follow C1, go left and then right and up and down, and then I follow C2. I go up and over and down and back. But in the middle of that, I went down and up along the same edge. That's unnecessary walking. So we don't do that. So if I add together C1 and C2, then I get C3. And if you're into mathematics, there's a way to make this precise using vector spaces or free abelian groups. But if you're not into those words, it also makes sense just as an intuitive concept. So this graph has, most important thing, 3 cycles. But if you know all the information about C1 and C2, then you know about C3 also. Now we are at the point where we can forget. So let's forget. We start with our Tate graph that we got from the knot. It has vertices, edges, and cycles. I know the vertices, I know the edges, I can read off the cycles. But then we're going to forget. We get vertex amnesia. That thing that remains, if I had a graph and then I get vertex amnesia, that thing is called a matroid. So a matroid has no vertices. It has edges. And I listed here the edges. So if you see there, the edges are numbered 1, 2, 3, 4, 5, 6. So we can list those edges. We no longer remember which one's connected to which one because we have forgotten the vertices. So that information is lost forever. But we remember the cycles. So I write down there are 3 cycles. C1 is E1, E2, E3 because it has the edges 1, 2, 3 in it. And C2 has the edges 3, 4, 5, 6 in it. And C3 has 1, 2, 4, 5, 6, everything but E3. So I have forgotten the vertices, but I still have a record of the edges and the cycles. Not quite enough. How could we possibly forget more? So from the matroid, we can now also get edge amnesia and only remember the cycles. So if I'm only remembering the cycles, what does that mean? I cannot remember which edges belong to each cycle because I have forgotten what an edge is. So what I need to remember is the length of each cycle and the amount that they intersected. So here, you see I have only written down C1 and C2, and that's because C3 is just C1 plus C2. Doesn't matter anymore. And for C1 and C2, I'm going to remember that C1 had length 3 because it was a triangle. C2 had length 4 because it was a square. And those are these numbers in my little table. So where you see C1 and C1, a 3, that's the length. When you see C2 and C2, a 4, that's the length of C2. And then there's that -1. I apologize, forget the minus sign. I just put that there because I want to be truthful. But, but sometimes truthful and helpful are not the same thing. C1 and C2 overlap in exactly one edge, right? That's where the two cycles meet. So that's what that 1 means. And the minus is that in the cycles that you go opposite ways. So I say at the bottom of the side, this is oversimplified, but it's morally true. This is how it works. So what we're going to do is do all this forgetting. So start with a knot, build the Tate graph, and then forget all the way to the lattice, which is just this little table of numbers. And this is a knot invariant. And you can kind of, if you remember how we put the John Nash edge on when we do a twist, that will no longer bother us because it's not part of any cycle. If it's just hanging off there, it's not part of a cycle, so we are going to forget it altogether. And all the other problems that I haven't gone into the detail of also disappear. This is a bona fide knot invariant. But is it a good one? It turns out it is. So this knot invariant almost completely distinguishes between alternating knots. What do I mean by distinguish? I mean, if I feed in different alternating knots, almost always I'm going to get different values. And that's not guaranteed. That's a very useful property that a knot invariant can have. That means that it's strong. I can use it for telling the difference between different knots. So what do I mean by almost completely? It distinguishes all alternating knots except for this one violent operation called mutation. What does that mean? A knot mutation is if I take the knot and I pick out a little circle in it, which intersects the knot only 4 times, just like this pink circle. And then what I'm going to do is I'm going to snip it at the 4 intersections. And once I have snipped it, I take that pink part and I flip it over. So I flipped it over and then I re-glue it. This is a mutilation, right? This is not gentle. It makes a knot into a different knot. But it's still something that you can do, and this invariant that we have built is blind to this particular kind of violence. So it's going to be able to tell me 2 alternating knots are different unless they are mutants of each other, unless I can get one from the other by performing this one operation. So this is a wonderful theorem from not too long ago, from the last decade. And when I first saw this theorem, I thought that I really liked it. I thought it was really beautiful. And what I really liked about it is the way in which it connects knot theory in graph theory and graph theory in a very original way. Not necessarily because of this Tate construction, because that's been around for quite a long time, but the particular theorem in graph theory that the proof used, that Josh Green used to show that this invariant completely distinguishes alternating knots, almost completely. That was a very creative sort of importation of a graph theory technique into knot theory. So when I saw this, I was wondering, can we make this stronger? Can we make this broader? Can we apply it in a setting where it had not been applied in its original form? And the answer is yes. And to be able to tell you about that, we have to take a little detour and do a puzzle together. So let's do a puzzle. How many of you have seen this puzzle before? A few? Excellent. So it's called the utilities puzzle. So imagine there are 3 families, and they live somewhere in the outback, and they need access to 3 utilities. The utilities are a well, a convenience store, and a wood pile where you go to collect firewood. So these families have kids, and they want to be able to send the kids to get the milk and the water and the firewood. And they don't want the kids to get lost. So they want to build paths from each house to each utility so that those paths don't cross. Can they do it? So think about it for 2 seconds, and then we'll decide by democracy. All right, democracy. Yes, they can. Few? No, they can't. Many. Many of us are right. Democracy works. So let's see. So let's say the blue house gets there first, wakes up earliest, and builds their 3 paths to all the utilities. Then the red house, wood pile is okay. For the shop, have to work a little bit harder. And for the shop, we have to take a detour, but we're still fine. And purple house, wood pile is okay, and the shop is okay. But see, to get to the well, it's a bit of a pickle, because this well is encircled by a red and blue cycle. And we know that now because we know all about cycles. So if you follow from the red house to the wood pile to the blue house to the shop down to the red house, that's a red and blue cycle. Inside it is the well. How on earth is the purple house going to build a path that gets inside that circle without crossing? No way. So that's too bad. But mathematicians have come up with a solution to this problem. So we suggest that these families move from Earth to a planet that's shaped more like a swim tube. Now, I see some of you are starting to doubt the applicability of, of this research, but I would like to invite you to play, because I think with a lot of basic research, you don't get to the really interesting stuff unless you're willing to play a little. So let's play. And imagine that they have moved to the donut-shaped or swim tube-shaped planet. And now the situation's better, because the blue, again, they woke up first. They are just early risers, so they built their paths. And then the red goes to the wood pile and to the well. And then they say, oh, let's have some fun, and go to the shop along the other side. Now, they're not crossing, right? Because that path is on the other side, the back side of the planet. So it's not a crossing. And then purple goes to the wood pile and the shop, and again, what looks like a crossing, not a crossing, because that red path is on the other side of the planet. And then they can get to the well by going around the middle hole of the swim tube. It worked. So we have solved this problem by moving to a different planet. And surprise, surprise, this is actually about graphs, right? That 3 houses and 3 utilities, those are the nodes. The paths are the edges. And this graph, this 3 houses and 3 utilities graph, this is a graph which cannot live on the plane, or in fact on a sphere either, but it can live on a swim tube shaped planet. And it's also about knots, because just as there are graphs which cannot live on Earth, only on swim tubes, there are also knots. And there are also other surfaces. Who has been to one of the water parks around Sydney or elsewhere? Yeah, who has gone down a water slide in a quadruple or triple swim tube? Few people, yeah. So there are surfaces which have more swim tube holes. And if we have a little bit of imagination, we can imagine that there are surfaces which have 157 swim tube holes. And there are knots living on those surfaces too. So what do these knots look like? I'm going to borrow you for a second. So now our knots can live not just in this room, but in the atmosphere of this swim tube planet. And that has more complexity because the knot can twist around itself, the string can knot with itself, but it can also knot around the dimensions of this swim tube shaped planet. So this here is an alternating knot. It's actually the same knot that's shown there. And let's see that it's alternating. It goes over and then under, and then over, and then back here, under, and then any more? Under, and then it gets back. So it's alternating. And if you look on this picture, you can also check it's over, under, over. And then see there where it goes on the other side of the planet, that's not a crossing. It's not crossing with itself. It's on the other side of the planet. So this is how knots can live on swim tubes. The question that I asked was, can we make the same knot invariant for knots which live on swim tubes or more complicated surfaces? So on first glance, we could, right? We could shade it in. We just shade it in on a donut, but that's fine. I have markers that draw on a donut, so that's OK. And then we put nodes, and we connect the nodes. And from the graph, we make the lattice. So that seems OK. But does it work? Will it actually give the same output when I feed in the same knot, just looking slightly different? And is it any good? Will it be good at distinguishing alternating knots on different surfaces? And this is the project that a couple years ago a team of us have done. And this team consists of, the person in the top left. The person in the bottom left is Hans Boden, who's a Canadian mathematician. And these two people are Tilda Wilkinson-Finch and Damien Lin, who I think are in the room. Can you stand up? So at the time, Damien was an honors student at the university, and he is now working on his research master's. And at the time, Tilda was a second-year undergraduate student, and now she's doing honors, working on her thesis with me, also on knots, but on different projects. And what we found is that indeed you can do this. You can do the same process. It does give you an invariant. Now, showing that it does give you an invariant, that's not obvious, because the techniques that worked to show that in just three-dimensional space, and just for knots in this room, didn't work the same way when we are in the atmosphere of torus-shaped planets, or swim tube-shaped planets, or other fancy-shaped planets. So we had to add some more to it to actually show that we are building a correct machine. And we also discovered that it's not quite as good at distinguishing alternating knots as its classical analog. So what turns out is that there are pairs, examples of pairs of knots around a double, triple swim tube, which are not mutants of each other, but this invariant will still output the same value. And Damien and Tilda were absolutely instrumental in coming up with an algorithm and writing code which actually computes the output of this machine so that we can compare and find these examples. By the way, this set of authors that you see here, it's Bowden, D, Lin, and Wilkinson. And you might think that it's in decreasing order of age, but it's not. It's in alphabetical order. And the D is me. In mathematics, we always list authors in alphabetical order. And we always, when we give talks, we don't put our own names, we just put our initial. And that's because we value everybody's contributions, no matter their age or seniority. All co-authors on a mathematical paper contribute significantly, and all the contributions are considered equally valuable. So the question that I still don't know the answer to, and some of the students who have worked with me since then have tried to find the answer, but we haven't succeeded so far, is whether we can strengthen this invariant so that it would be as good as the one for just knots in the room rather than knots on surfaces. And that's all I wanted to say. While we get into the questions, enjoy this slideshow of what it's like to do research in math. And that's it. Thank you.